All right, trying something a little bit different here today and skipping the intro. So it feels like the training wheels are off, but hopefully everything is going well. I'm always watching the stream off to the side here come through on YouTube, and with a few second delay, it always is a little bit disorienting. But, anyways, Black Hat DEF CON Hacker Summer Camp, as it's affectionately referred to, has wrapped up, and going to continue with the live streams here. Cerberus is joining today to talk about Binlex malware hunting, looking for bite patterns using, I guess, what would you call that? I'll let her describe it then, I guess, since I'm missing how I exactly want to say it. But we'll talk about that in just a moment. Next week, Duncan Ogilvy, X64 debug creator, pretty sure it's next week, is going to be on the live stream talking about the latest features with X64 debug and some pretty cool stuff there. Types, be able to have types in WinDebug. So that should be pretty cool to see if you haven't checked that out. Anyways, welcome to the stream today. Thanks for joining. And for anyone who's catching this on the recording, let's get started. Okay, so Cerberus, thank you for taking time to join. I had the thing that I wanted to say all ready to go, and then the time came to say it, and I forgot it. So I was going to introduce Binlex, and this is it's a really cool. I have to admit I haven't been a user yet, but I really love the idea, and the idea has kind of somewhat sort of crossed my mind over the years. There was a commercial company, and I also have been drawing a blank on who that company is now, but yeah, Intezer, that's it. It seems like there maybe is kind of a sort of overlap there. So, but there's no point in having me ramble about your project when you are the author and the creator. So you might as well tell us everything we need to know about it. So welcome to the channel. Thank you to the stream, and thank you for joining today.
Thank you very much for having me, and I'm looking forward to telling you guys all about the history of developing Binlex and where it came from and what you might be able to use it for.
Yeah. I'm definitely interested on all fronts. The practical side of it, because detecting things. Yeah, usually I rely on Flirt from IDA to do the bulk of my my detection,
Yeah.
for better or for worse. And I'm also really curious where you got the idea. I mean, it just seems like the more I dug into the GitHub and the project, and it just seems like you've poured a lot of effort into this. So I'm anxious to see it and hear more about the story. So, besides Binlex, I don't know, you stream often. Do you still stream often? I know you were streaming often.
I was streaming often. Life stuff came up, but
Okay.
yeah. And then just lately, I've been super busy with work, and I'm building a server rack in my house. I have a
Oh,
huge
okay.
NAS I'm building over there on the other side of the room because I want to be able to serve some stuff on my streams and stuff eventually too. So
Okay.
yeah, and also provide people perhaps downloads to my videos off of YouTube and make them available for everybody.
Yeah. I YouTube probably. I remember a post before you left. They were hitting a lot of cybersecurity creators hard for things. It seems
Yep.
like a lot of times they get you with the links. I know Brad
Yep.
Duncan, if you know malware traffic analysis, he went through a whole thing. Because if YouTube doesn't get you, then the whole safe browsing thing does. And I know
Yep.
he's got the
Yep.
site where he was putting all of his malware artifacts, packet captures into zips, and just using the good old standard infected. But
Yep.
that became such a hassle, and it is like true for everybody that tries to share things now. I know I try to share things, and I have to always put different passwords on and
And
remember.
people laughed in an interview when I hosted my original blog on Tor.
Hmm.
Not laughing now, are we? That's exactly why I put it there years ago. So I
Yeah.
may do that again.
Yeah. You might have to. It gets to be challenge. It sure gets to be challenging. So yeah, I can see where that would be frustrating, and then certainly having the ability. I guess I don't use YouTube all that often as a consumer. So sometimes I get a little disconnected from the everyday experience of using it. But I don't think you can download videos, and oftentimes that's pretty handy to have an MP4 of your video to review. So
I turned it up a little bit more on my end.
okay, yeah,
Is
now
that a little
you're.
bit better? Too hot?
Let me bring you down a little bit.
How's
Yeah.
that?
Oh
Is that
yeah,
better than
that's
it
pretty
was?
good. That's good. Yeah.
All right. Cool. Um,
Oh yeah, I
I'm re-
see somebody mentioned in chat we've got a little low on the volume. Yeah, thanks
yeah,
for pointing that out, Drew, and welcome.
I'm ready to start whenever you're ready.
Yeah, I'm ready. I can. I've mastered the art of small talk years ago from teaching. So if I'm not careful, I'll just keep going.
I run a couple of mentorships here and there, so yeah, it's teaching sometimes is quite fun. Although I don't, not a teacher.
Yeah.
All right,
Yeah.
so Binlex,
Let's
let's get
see.
into it. Um, so, turning disassembly into genomic traits, enabling you to write better code-based YARA rules. That's basically going to be a discussion. Of course, it can be used for much more than that because it's kind of a framework, if you will. I've rewritten it from into Rust, and I'll go through the history of it, how it works. I was already introduced, so I'm Cerberus. I am a senior security researcher at an undisclosed location working. Just imagine me inside lead lined walls, like 500 feet underground. That sounds cooler than what I actually do, so I thought let's just say that.
Yeah.
So, yeah, what is Binlex? So, bin is for binary, lex is for lexing or parsing, and then genetic. This is what I break it out to into its individual properties and components of each specific trait. And framework. So framework, what you'll see is that we have an API that we can leverage in Binlex to do some really cool and fun and wacky things with patterns and blocks, functions, etc. inside of binaries. Right? So why should I use Binlex? Or more importantly, why should you use Binlex and contribute to the project? It allows you to craft code-based rules directly from a disassembled code, and it's wildcarded for you. So having to go into, if you want to make a really good code-based rule to pick up on something, and it's like, okay, so in Ghidra, I think they have a plugin. You can go in, you select it, and then you select the points, and then you grab the code, right, and wildcard what you want. In IDA, there might be some plugins, although I think they're not as great. And then, right, so there's some ability to do that, but this is more of a framework to do that at a more kind of automated, in a more automated, scriptable kind of way. Detect and identify threats by matching similar binary patterns across multiple binaries or multiple malware samples. You can do that as well. And maybe when we get to a demo, I'll show you how we're going to do that. Leverage genetic style analysis to find binary level similarities across malware samples. So, yeah. So one of the things I found when I was working on some of this stuff, running YARA rules, I'd have one sample I was working on, then a folder on the other hand, doing like A/B comparisons, running YARA rules, and after a bit, like it just got kind of to be a pain. Right? It's like opening IDA in one, open the IDA in the other, put them side by side. Okay, that just drove me absolutely mad. And I said, there must
Yeah.
be a better way.
Pain is the true. Oh man, I'm having a day. I can't remember anything I want to say, but like the true driver of innovation. pain,
Yeah,
pain and inconvenience. There's a more elegant way of saying that, but so often that's the case.
it came out of pain while working. So it's malware genomics that you can essentially grep. So imagine grep for like malware and YARA patterns and binaries. It sounds kind of wild, but you'll see what I mean because we got some super crazy shell commands I'm going to show you that that may make your eyes bleed, but will also make you happy. So before I get into it, There's code similarity copium. This is a super based opinion of mine, but these are some of the things that I have seen regarding binary similarity. I included commercial protectors in my analysis. I'm sure the malware family will be recognized regardless. Excellent. VirusTotal told me it was that malware family, so I proceeded anyway. Perfect. It's a different architecture and compiler, but I'm sure there will be absolutely no issues whatsoever. Excellent. Code is obfuscated, but I'm sure the malware family will continue to be detected properly. So what I'm trying to say is before we get into this, there is no silver bullet, right? There's so many different ways to approach this type of problem. I'm trying to make a little framework to kind of address it, but address it in a way that allows it to be flexible for you to get your job done in your own specific way. So TLDR is the halting problem, does not care about your feelings, right? That's just the way it is, or the undecidability problem in malware detection. Does not care how you feel. You could cope as much as you want, but we're going to try to be realistic. With that out of the way, developing Binlex, this is an overview. So we take an executable and we find its entry points. So those entry points can be in many locations, right? So generally you do a heuristically identify these in like vtables, or look at the exported functions that happen to be with the binary, or do a linear pass to identify some of these entry points heuristically. Once those initial entry points are identified, then going ahead and disassembling those recursively with a recursive descent algorithm, right? But multi-threaded, we'll see, right? Then that data gets stored into a control flow graph. So basically it's just kind of linear map data where it's like address and instruction, and then each one of those have the properties specific to each one that is important to Binlex. And then we can parse that CFG out into its individual genetic traits. All right, that was a lot, but that's the overview. So I talked about heuristics, right, for a while for identifying entry points. So in Binlex, there's a linear sweep. This algorithm was helped out with a bit by Sergey from OA Labs as part of a big, I think it was a Geek Week or some sort of event had happened, which was kind of fun. So it has a valid jump threshold, valid instruction threshold. It skips traps and privilege instructions, and it checks for call instructions and if they point to executable code. So it's just kind of linearly going over the executable sections in the binary, and then using these heuristics to then identify, is this likely an address that this call goes to that is valid, right? And can I add that to the queue? Does it make sense? So very common practice for disassembling to use a linear pass to heuristically gain your entry points. The next part is if you program in C and C++, there's vtables as well to be concerned about. So with vtables, in the case here, I'm only supporting them right now for portable executables, is go over the read-only sections of the binary and scan for 4-byte aligned addresses and check to see if those are within the executable range. So we're looking for, in read-only data sections, for pointers to executable code in executable sections. Track the number of hits I get. I find 6 plus, 6 or more is kind of the sweet spot without, you know, completely, wrecking yourself with false positives. And then in queue. Yes, will there be some missed? Probably. So again, it comes down to undecidability problem, right? You got to kind of pick the best one that works the most of the time with little drawbacks. And so those will then be queued onto for the entry points at that point. Do we have any comments in the chat? Or
No, nothing yet.
good?
So yeah, feel free to fire away questions as we go if you had anyone, and then I'll make sure to thread those in.
Okay.
I think there's
Awesome.
just a lot of graph digestion right now.
Yep. That's why, if I need to be interrupted or if you want to ask a clarifying question, feel free.
No, it's all making sense. And like the power of the visual, it would have been, I think, very easy to put this content in bullets, and the graphs really do help tremendously. So data visualizations for the win.
Awesome. It's just a mermaid. So recursive assembly is next, right? So we've populated, right, our initial queue. I kind of glazed over a bit. There's like exported functions and other things like TLS callbacks potentially and other specifications, and I could go on forever. Either way, you have a set of ways to add to your initial queue of entry points. So we start there. We in queue, right, those entry points, right? If it is empty, then we're done. If it's not, we dequeue it and send it to the disassembler. And the disassembler will then be like, all right, well, let's disassemble instruction. Is there a jump or a call? Then we in queue the target, right, address as needed. Add the next instruction to the address queue, and we just keep on recursively going and going and going. Using recursive descent. So every time you're disassembling an instruction, you're making a decision, right? Is this a jump? Is it a call? Is this a control flow change? Where does it go? What's the fall through address? What's the jump to address? There's more complexities in our jump tables, which this doesn't currently support yet. But that's something that gets more complex, where you may want to lift to intermediate representation and semantics, and we can talk about that later towards the end as a more advanced topic.
We do have some questions if you're ready.
Yeah. Go for it.
So Casually Joseph is asking about, is this similar to Microsoft's IRE project? And I have not heard of IRE, so I don't know.
I have not heard of IRE.
Okay, that makes two of us.
We can Google it.
Yeah, I always have a window open. New prototype AI system from Microsoft designed to autonomously reverse engineer software and detect malware.
Okay.
Autonomous reverse
is it on
engineering, LLMs, high-level analysis, promising results. Yeah, I'm just getting the elevator pitch of it, so I don't know how it's doing it.
If it's not on GitHub and open source, it doesn't exist, right?
Right.
Ideally, I like things to be available for everybody.
Yeah. So it probably is not quite the same. It looks like this is more of a, well, I guess I don't know. Classifying software without prior knowledge of its origin and purpose.
It sounds like it has some. So Binlex is kind of trying to be more of a framework as opposed to a full stop solution, right? Mm-hmm. So there's perhaps a bit of a difference there. But yeah, we'll keep going.
Keep going. Okay, there's one other question.
Yep.
From LinkedIn. I'm not sure if I
Go
quite
for it.
understand, but is CFG. So we're talking control flow graph, and I'm guessing CFF is control flow flattening.
So control flow flattening would be the process of deobfuscating a control flow. So for example, like if you see, um, like if you take a for loop, for example, and you have a switch case in it, this is just breaking it out, and each one of those have a state, right?
Hmm.
You can resolve those states and then flatten the control flow, for example. There's many different ways you can do control flow obfuscation. But it's control flow flattening is a process of flattening the control flow, typically through obfuscation. It can also be a compiler type optimization of some kind as well. But that's, again, quite different from what we're looking at here when we're explaining the control flow graph
Yeah.
with Binlex.
When you encounter binaries with control flow flattening, it is. I mean, do you do anything special to try to identify, observe, or unflatten, or like reinstitute the original control flow? And
So
that seems like a hard problem.
okay,
So
so if you were speaking about control flow flattening as a type of obfuscation, like obfuscator, like it's completely flat, um, that would I haven't seen any of those in the wild or worked on them. But what I have worked on is taking obfuscated control flow and then flattening it myself. That I have done. Um, but if you were to do that from like obfuscator, for example, it's been flattened as an obfuscation technique. Um, your best bet for that is probably to look at intermediate representation and use some advanced tooling around that, and it would be an absolute pain in the neck.
yeah.
Yeah.
Someone suggested it maybe more like Glimpse, but here's another project that I am not familiar with. So I guess we'll have to just save the. If I'm not familiar, I don't know if you've heard of Glimpse, glimpse.re.
No, have not.
Yeah, I haven't either. So I guess we'll have to save
Glimpse.
that for another time. That doesn't look right, does it? Real estate development insights. Yeah, maybe it's. Let's see, Glimpse is a software solution for automated reverse engineering and malware analysis.
All right.
Well,
And
yeah. Anyways, sorry. Good questions. Great questions. Keep them coming. But we'll get back to the slides here.
yep. So Binlex is assembling at speed. So Binlex now does something really interesting to disassemble. We use it uses sparse files. So we have our logical file, right? We have data, a gap of like null bytes, data, gap, data. And if you think of how something is mapped into virtual memory, it's much like this. But with sparse files, the data that's there, data, one of these blocks marked data, they exist as data on disk, but the ones marked with these gaps here, like null bytes, so sparse, doesn't use up. Say I have a gigabyte, right, in this first gap, right, of null bytes. In a sparse file, they basically don't exist. There might be some metadata to represent its size, but it's only the size of the data blocks and maybe some metadata that defines the size of the entire file, which is super cool for doing some mapping of virtual images prior to running a disassembler against it. I also added to this caching for repeat disassembly for extra speed as well. And accessing these sparse files is like mapping the entire portable executable image to disk and then accessing it using mmap. So you can access it for disassembly like a raw pointer, and you're not using memory really all that much to access it. But you can access it as a raw pointer for disassembly, which can go pretty quickly and allows you to treat everything just like a virtual image, as if it was loaded into memory when it's actually not. Does that make sense?
Yeah, I think so.
Okay.
Yeah.
Yeah, sparse files, for those who don't know, it's something that Windows implements in its operating system. Mac OS has it, and Linux has it as well.
I always say it's a great like when I give a workshop or a training, when I learn something, and of course these live streams are meant for me to learn a lot. I always learn a lot. So, yeah, sparse files. I have not come across those either. It's
Yep.
amazing. Some days I don't feel like I computer at all. I don't know. I don't know how I miss all of this stuff all the time.
Yep. So the next part of Binlex is normalization, right? So we take something like this, right? Um, and then we break it down, get rid of these wildcarded nibbles, and then we get a vector, right? So it's kind of like the vectorization of these patterns as well. Binlex does provide. It also does some cyclomatic complexity detection as well, where we're calculating the complexity of a function. So in this case, it's edges minus nodes plus 2 times the number of components. It helps with obfuscation detection. So one thing I've done with this before is Emotet had an obfuscator that they run, but it had a weakness because part of that obfuscator was static, right? But it was custom, but it was static. So using this, I was able to identify, well, what the hell is this little bit of code, right? And well, apparently my Yara rule ran in the back of Unpack Me for like ever. And like they never caught on, which was kind of cool. So being able to identify obfuscation can also allow you to find weaknesses in obfuscators as well, if that makes sense.
Yeah. Yeah. Some more questions, but I'll save them because they're not quite pertinent to this. So questions. I'll get to your questions in just a moment.
The other thing as well is entropy. So checking the entropy of code can help with identifying, well, is it obfuscated or not, right? If you want to match on something reliably, right, you may decide to filter based on entropy and be able to make some decisions there.
Is that something you can set then when you're using Binlex?
Yep.
Yep. Okay.
Yep. I'll show you all of that.
Okay.
So now I'm going to talk about the development history a little bit. So it started in C. Before, it would just simply load a binary, iterate the sections, and do a linear disassemble on the entire section. That's it. And it would then spit out these patterns. There was, did not handle non-contiguous functions, had no vtable support, no Python API. But as stupid as it was, it made a lot of Yara rules,
Okay.
which is great. The next iteration was in C and C++. The main limitation I encountered with C and C++ with it was, yes, doing recursive disassembly, but the implementation of doing this in a threaded capacity was kind of a pain. And further, as well, the ability to provide it cross-platform was also a pain because each C++ build environment had its own quirks and drove me nuts. So for a side project you're not getting paid for, that was no fun at all. So moving from there, now I've moved everything over into Rust. It does recursive disassembling with thread safe queues, and all of that has vtable scanning, like I said. Is able to normalize blocks and functions, and it's multi-threaded. And sure, it probably was a skill issue last time, but perhaps. But this time around, for a hobby project, that I'm not getting paid for, I figured, well, Rust saves me a butt ton of time and makes threading easy, so why not? I don't like reversing Rust. I do like writing it, though.
Sure. Okay.
Um, core functionality, so recursive disassembler. Um, so it's self-contained. You don't need to need IDA to start using it. So it's not like some of these other tools where like you need to run it as a plugin. Sorry about my dog.
No problem.
Um,
I scheduled the kids to bust in about 10 minutes, so
the command line interface is fast, scriptable, and shell friendly. Your JSON output is structured, and you have a Python API. And I started creating a bit of a IDA plugin so you can mess with that with some of your IDA projects if you wish to as well. So I'm going to start talking about genetics, hierarchy, and their definitions.
maybe
So
I could ask you real quick. So, question from
yeah,
LinkedIn,
yeah.
because I might have missed this myself. Is this Intel only? Do you support ARM or other architectures? And I guess the question is, are you going to support in the IoT space, such as RISC or MIPS?
So there is the ability to support RISC and MIPS. There's one PR that's currently in for, I think it's ARM. It's not fully completed as of yet, but the initial starts of it is there. And yes, other architectures such as RISC, MIPS, and whatever can be used. If Capstone supports it, then it can be added. And I would encourage the person to ask that question to feel free to hop on to the GitHub page. There's a PR there from one individual if you wish to contribute to ARM a little bit. Some of the works is already there, so feel free to add a little bit and I'll review it and probably merge it.
Awesome. Okay. I see it open right now. Only 2 pull requests, so easy to find.
Exactly. Yeah.
Yeah. Awesome. Okay.
All right. So genome, complete set of genetic material, full blueprint of the system. So this includes one or more chromosomes. Chromosome is a complete sequence of material, one or more pairs. Pairs contain 2 genes, and I'll break these down here eventually. So as you can see, genome is kind of like our full JSON object that we're going to get back. Chromosome is kind of like what the patterns exist in. And then each one of those, I look at a byte as a pair. And then a pair has 2 genes, and they're simply just hex with a wildcard, and that's it. So this is how this kind of translates into the binary world. So this chromosome there, like dead beef with the question marks, is a complete sequence of an instruction block or function. The pairs are the individual bytes. You can see they're split out there just like that. And then the genes, you can see they're then split out like that. So that's kind of the genetic language that I use with Binlex. Yeah. So this is an example of what it looks like. It's simplified here, but you get your bytes there. You get, where it's going to, what its address is, what the architecture is. You also get min hashes, SHA-256 hashes, and TLSH hashes, as well as the entropy and cross references. There's also attributes for additional attributes that you can add to the JSON as well for additional properties like function symbols and things like that. So IDA right now, I've been experimenting with this, is going from IDA essentially or whatever, or Binlex API, and sending it to a graph neural network and storing these in a vector database. So these are the endpoints that you can experiment with. You can list the databases, and these are partitioned by their architecture. And you can search your vector database for the code that you're working with. So it's kind of like a search engine for functions. So instead of having, for example, a flirt signature, like he had mentioned towards the start, you can kind of take and distill it down to a vector using PCA and some other algorithms, stored in a vector database, right? And then you can query that vector database for that. So instead of having to do matching off of every single function, whatever, it'll just give you the top, whatever many that you want that matched almost instantaneously for
Okay.
many samples, which is kind of cool.
Yeah.
So GNN embeddings, it extracts some semantic vector embeddings, right, from function or blocks. Uses a graph neural network with Torch, and so it's like a two-layer G. And again, I'm not an expert on these. These are from papers I've read and talks I've listened to. That I've added some of this stuff in there to experiment with, and I I would say have a look and experiment with it as well. And if you're a data scientist and not someone who reverses malware day to day, feel free to contribute. For blocks, I'm using instruction count, entropy, control flow, and edges, and a histogram of the features. For functions, I'm also collecting cyclomatic complexity and average instructions per block. And yeah, so pretty fun storing it in a vector database to see what I can get out of it. But one of the funnest things to do with Binlex is to use the command line tool. So you can look in a sample, or look for a sample, let's say in a directory. You can then go ahead and input that to Binlex and then parse the JSON with JQ, for example. So you want functions, contiguous ones, unique them, and get the top, right, number of repeating ones, right, like right out of that. And then you can also make a YAR rule out of it by piping it into this, and then you can immediately get our YAR rule, which is pretty cool. But you can get even more advanced with this, right? You can say, oh, well, that'll give you a lot of false positives. Well, you can query some of these hunting rules that you make against goodware and then pare them down and only get the really good ones. And you can use the Python API to automate that if you wish. You can also provide Binlex with symbols. So for Risen or Radar, you can run this and it'll take the functions from its what it identifies, and then if you pipe it into the BL Risen tool, it makes into a format Binlex accepts a standard input, and it'll use those to populate the initial disassembly queue for functions to help it out. Yeah, and it will also receive the symbols from that as well and add them as attributes as function names. And then Ghidra, you can run this. Ghidra is a bit jank, so its headless output is almost right. At the time of writing this this year, I had to put this in there because the output was not truly headless. Had other kind of output that was just screwing things up. So maybe that's fixed now, but this is how you would go about doing that. So the other thing is if you export it and you add in your attributes, function names or whatever, you can look for those and see if it starts with malware, for example. So if you do that and you export it, for example, from IDA, you could look for those prefixed function names and get all the traits of blocks and function right stuff right back for you and make and insane YAR rule, like it was not written by a human being, um, which is kind of fun, all in the console. This is the main window. So you would use the export here to export it. And the search methodology for the vector database is GNN score plus min hash score over 2. So it uses the vector database first, and then from what it gets back, it double checks that with actual similarity hashing. So you're kind of getting a twofer with that. It's like, okay, well, what? Uh-oh.
That sounds serious.
Yeah, it is. We have wildfires here, and yeah, it's not for me though.
Okay. Well, that's good.
Thank God.
Yeah. Are you
All right, I'm good. I'm going
okay?
to continue.
Good. Good.
So, yeah, so it averaged those out. So trying to give you the best of both worlds there. So here you can set a size ratio. If the size is off, not too far off, you can set the min hash ratio as well, and your similarity using the graph neural network, and combined, what you get back. And I have it in here. You can copy like vectors for, like, you right click on a block, you hit copy block, and then you can paste it into your database and search it. It's kind of cool.
Yeah.
And copy hex patterns, or hex and or patterns as well, to help you write your rules. I'll talk about the API because I know you have a hard one on the hour here. Go as quickly as I can. So this is how you would use it in Python. So you set your config to 16 threads, you load the PE, you grab the image, right? And then the mmap, which gives you the raw pointer, right? And then you point that to the disassembler. And since the disassembler is file format agnostic, as in that you're passing the entire virtual image to the disassembler. All it knows is what ranges are executable based on what you told it, where the image lies, what architecture it is, and how you want to do it with the config. That's it. So the disassembler could care less about what file format it is, right? As you already gained that stuff before. Then you build your control flow graph, and then disassemble control flow, and you're off to the races. So you can iterate from these levels of abstraction. So from functions to blocks to instructions to pairs. Well, I talked about that. To genes, individual nibbles. So if you want to talk about more binary, be function, block, instruction, right? Then byte, then nibble. Right? I don't know if that seems wild, but that's kind of the hierarchy.
Sure.
You can also do comparisons. So LHS is for left-hand side, RHS is for right-hand side, which is, I guess, common in discussions of genetics. But here we iterate over left-hand side functions, and then we directly compare the right-hand functions against each other. You would have some other logic in here to decide when you want to perform a comparison or not, but essentially that is how that works.
Okay.
As well, you can do mutations as well. So you can take each one of these chromosomes, right? And you can mutate them to different, right, wild-carded traits, which could be useful for performing some more genetic programming to look for variants of things if you decided to go down that route. So this is a possible workflow. Use Python to extract malware family genomes. apply custom filtering for cyclomatic complexity, etc. Remove goodware from your goodware data set against those patterns. Remove other malware families that are not that malware family you're looking for. Perform mutations if you so desire. Create a YARA rule, hunt, and detect. So stay away from code similarity copium. And if you write YARA rules, feel free to make them your own, right? And use some automated tools to assist you to get there. There are some tools that I think you can just put something in and just, you press one or two buttons and then you leave for like hours on end. And then when you come back, a YARA rule may be generated for you. It could be good, it could be bad. I myself like a hybrid approach where I use a little bit of my human intuition and a little bit of programming to get me to my final product. So if you do use Binlex and use in a presentation or something like that, feel free to add this particular citation. If you do decide to publish research on it as well, it's always greatly appreciated. I think now what I'll do is get into a bit of a command line demo. How does that sound?
Yeah, that sounds great.
So Binlex is here. Right, so this is linked. All you need to do is ensure you have Rust installed with cargo, and it's simply cargo build release. That's it. Way less complicated, of course, than what we had previously with other stuff or the C++ framework. So I have two samples here. I can run this one at 16 threads and pipe it in the JQ. And this is the output. I know it's a lot. It's like staring into the matrix, but you can see here we have this one's of type block. We have its address, virtual address. We have where it goes next, which is the fall through, right? And then where it jumps to, how many edges, is it a conditional or not a conditional? We have the pattern, right? We have the feature, which is the vector, which is normalized, right? Which we talked about. We have the entropy, and we have the SHA-256, the min hash, which is hashing for smaller sets of data, and no TLSH because it didn't satisfy the requirements, the size, the actual bytes, if it references any functions, what the blocks implicated are, now how many instructions are in there, right? And the attributes. In this case, this is a TLSH of the entire file. That's SHA-256 of the file. That's the size of the file and its full entropy, right? So you get a lot in each one of these. So you can also do filtering. So we can do a select type is equal to function, right? And we get this out. Let me simplify this, -C. This is for every line, right? That might be a little much. We can -C, take the first one, and then pipe that in the JQ again. All right, so, and there we go. So this is a function, right? Here are the function bytes. They are wildcarded at the resolution of nibbles to get rid of the addressing, right? So that if the compile changes for another binary, so as long as these everything is good, this should continue to match. Then the normalized vector. So if you're a data scientist, that might be applicable to you. Entropy, SHA-256, here's a min hash, right? And then it should also contain some blocks here. Yeah. Okay. Yeah. And blocks, there's only one, I guess, because perhaps it's a function that starts with this is only a singular block, which is perfectly fine, right? So now how would you go ahead and make a YAR rule, for example? So we can take this, say we're looking for functions, and contiguous means that it's all straight, right? It's all one big blob contiguously in the binary. There are functions that you can have that aren't contiguous, where some of it's here, some of it's there, some of it's somewhere else. Sometimes it's a compiler optimization, and then other times it's just purely obfuscation. So, and that's very important when you write YAR rules, because if it's non-contiguous and you just pull out all the bytes for the function, it's not contiguous at all, you make the YAR rule, it's not going to match. Because guess what? They're not a blob, right? And so we can do that. And now let's go ahead and get the pattern out of there. So these are the patterns, right? YAR patterns. So then we can do, let's say -r for raw, so that puts them out like that. And we can say and dot size is greater than 32, and dot size is less than 64 maybe. And then we have that reduced. Pretty cool. And so you can see there's some here that are pretty much similar. So I actually just recently added something as a tip. So here, so you can actually collapse these, I believe, by down here, a big readme. So this crazy awk command.
That's
So
the
these-
sign of a well-maintained project.
Sorry?
The big readme. It's the sign of a well-maintained project.
So some of these should be collapsed now. And then, yeah, it seems to be less, right? So wildcard more, right? And trying to combine them. All right, so we can sort unique that again. And this is what we get. And we can do, take 10 maybe. So these would be the top 10 here. So we can then pipe that to BL Yara, right? Give it a name, I'll test, press enter. Interesting, right? We just made a hunting rule almost immediately. Now, like I said, depending on your specific situation, depending on the sample and the context, this is kind of just a dummy example. You can come up with all kinds of cool ways that you can do this. So let's put that file. Boom.
Yeah, very cool.
Right? So, yeah, it can be very, very fun. So the other thing that we can do, well, I think we're at 5 minutes left, so
Yeah.
not very much. So maybe you're
And all
gonna tell me
that-
to wrap it up.
That function information contains the original address that sequence, whatever that, whatever that data came from. So if you wanted to go into IDA and actually look at the code associated with the pipe patterns, you could very easily pivot into that. Or I suppose the plugin would make our plugin, like an IDA plugin, would make that easier.
If you're really that concerned and like doing this shelling stuff here is like not enough for you, you
Yeah.
can always go straight into the API. There's even a Rust API if you want to compile your own to do this. By the way, the cool thing is that I support disassembling and getting patterns out of .NET binaries.
I was going to ask you about that. That's really cool too. Okay.
I don't have a .NET binary for the demo here today, but I should say .NET. Here. Yep. So you would, simply go ahead and run it, and it should disassemble it. There's a little bit of different stuff you need to do here for the setup because of the format, but other than that, That's it.
Hmm.
Binlex should identify your sample is .NET off the cuff, so you should be able to do binlex-I your .NET sample. That's it, and you
Cool.
should get your patterns back wildcarded for you.
Okay. And that uses the bytecode then, the .NET bytecode?
Yep, yeah.
Yeah. Very
I
cool.
wrote the disassembler myself. Uh, so that would be in here. Disassemblers, custom, CIL,
Huh. Very cool.
and here's all the mnemonics, right? I
Yeah.
went through and painstakingly did all of this. And then in here as well is the definition of an instruction, and then here's the disassembler, and I've made it.
Hmm.
I made it with the same principles as the capstone disassembler as well.
Awesome. Okay. Very, very cool.
Yep.
Yeah, I did. I didn't mention at the beginning, but I have to be a kid shuffler, and so I have a harder break than usual today. So we've got a little. We can go a little bit over, but too much, and I'll have kids barging in here.
So I think now would be the time for wrap up questions, maybe.
Yeah, probably. Otherwise, we run the risk of rushing through something. There's always another live stream if you're up for it, because I have a
Yeah.
feeling that this could be a fun project to explore. Over, I mean, yeah. So I guess the best way to get started is probably what you just demoed. Is just to get
The
some
best way
samples.
to get started, just run it in the shell, get some stuff back, automate it, help you with getting some of the stuff out of some samples you're working on. That's a good way to just get started with it, to
Okay.
be honest. Yeah.
So, and it looks like with the cargo build and all that, I'm not, I'm with you. I don't like to reverse Rust, but I don't write a lot of Rust either. So, it looks like that's a pretty straightforward process, well documented on the GitHub. Yeah.
There's tons of documentation on the very first page. There is a config file that you can do, and just for sanity's sake, this was kernel 32 just for the demo. So samples, this one, we can set it to minimal. Right, and 500 and some millis for that one, and we can say I'm flexing. And 2,380 functions, 754 milliseconds. That includes the parsing with JQ. Take that. 16 threads. You're
Yeah.
welcome.
Yeah. Yeah.
Less than a
Awesome.
second. So if you want to do some quick scripting, this is the place to do it.
Okay. I have a feeling, yeah, I know whenever I open IDA and it's just chugging along that I'm in for a hell of a time with whatever I'm looking at. So it could probably use a performance boost like this.
Well, it's only using it for a certain use case, right? So that kind of helps its speed.
Mm-hmm.
Yeah.
Questions. And if anyone has any questions, I guess this is going to probably have to turn into last call. If you catch the recording and have questions after that, I'll have comments open. If I can't help out providing an answer, which likely I can't, I know who to get in contact with and let them know. But yeah, if any questions, if not, we're probably going to be wrapping up here pretty soon. A little bit of a delay here on the stream, so I'm just trying to give everybody a second for restream to catch up with the platforms. In the meantime, this looks like an amazing tool. I'm looking forward to playing around with it myself and finding ways to. I like writing Yara to some degree. I'm not an avid Yara rule writer, but this looks like a way to make that process a little less painstaking. And so I'm really looking forward to. So thanks for all your work and effort on this. When did you start creating this project?
I would say I started creating it. Oh my gosh, it's been over 3 years now. So I
Okay.
think I kind of like 20, kind of before the pandemic. I think I started in C or something. It was a while ago, 3 4 years ago now. So it's something that I've been picking at here and there in my spare time to, you know, provide something that's open. And
Hmm.
I'm working with someone else here and there, whom is going to be helping with the lifting of some of this stuff to VEX intermediate representation. So that's where it gets more architecture agnostic
Yeah.
for similarity analysis and more advanced assembling stuff if you so want it. So eventually, that's where I hope to get it and to working on some IR stuff as well. So
Okay.
it's still useful.
Well,
And I look forward to any contributors who wish to contribute. And yeah.
yeah. Yeah. Binlex on GitHub. So looks like it would be easy to become a part of the contributor pool. So definitely check that out. A
Yep.
little past the top of the hour, so I think I'm going to have to call it. Thank you again, Cerberus, for your time and all your efforts here and all that you've given back to the community. It's always great to be able to say thank you personally. So hopefully we can do this again sometime. But until then, I guess any last comments, I'll leave it up to you, and then we'll hit end stream.
I'd like to say thank you for having me, Josh. Seeing your videos, very professional and very educational. Highly recommended, of course. Watch them here and there as well. And yeah, thank you for having me, and thank you all for joining.
Yeah. All right. Thank you very much. Appreciate it. All right. Thanks, everyone. I'll see you all next week. I did check the calendar. Duncan will be on talking the latest features for x64 debug. So come check it out. Types in x64 debug. I can't wait. All right. Till then.